Good evening. Yes, this is your user face, Michael. Today or this evening, I wanted to continue with a bit of explanation or sharing my encounters with bridge structures, especially the pre-stressing system or post-tensioning or post-tension bridges or pre-stress concrete bridges. In this knowledge sharing, I have a three-span three-span, three-cells box girder, continuous box girder, post-tension bridge, which the deck is bearing on two support. These are the pier support round, and then your pile caps, and then your piles. And this ends, this end here and this end, they are representing, this support system are representing abutment. We could actually as well model the abutment to its fullness, but I think because of time and maybe just choice made, decided to only do the pier support system, and then later on you do that. So this is box girder. We can actually look at the section of the deck system, quite a number. You can actually look at this. So that is how the middle deck system are. These three cells. So the whole thing is this one is the outer section. This and the middle web. These are two middle webs, and these are exterior webs. So it's about 12 meters per width, and then this is going to have crash barrier and the rest. So I think if I may take you to this is how it looks like. Okay, that's how it looks like. You have the bridge. You see the side layout. This is the bridge crossing here, and under here you have like a runabout, and then this is the lower level, and this is where the bridge is, and that is the bridge. The three span 30, 45, and 30. The bridge cast in place post tension continuous box girder. Live load is you're using Eurocode SV196 and other loading. Total width is 19, including the crash barriers and parapets. The spans are 30, 45, 30. It's not skewed, it is at 90, as you can see here. And the box girder depth variable linear starting from 2 at the support towards the mid span, you get 1.35. And when you read other texts or references, which I can quickly give it to you, we have a design of pre-stressed concrete by R.I. Gilbert and N.C. Micoboro, School of Civil Engineering, University of South Wales, Sydney, Australia. You read that book. I'm going to share with you the detail later on of the authors. There's another one which is a pre-stressed concrete design, second edition by M.K. Hurst. Those are some of the reading that you need. There are quite a lot of authors that text references that you can get on Script or any other source on the internet. You can buy some from Amazon and others. There's also structure engineering documentation, concrete box girder bridges by Skolike and Chief. So those are some of the, so they will give you almost this requirement they're indicating here, like it is 2 meter 1.3. What are the span depth ratios you consider when you are coming up with the section. So at the preliminary stage, you have to design, you have to check all those preliminary checks to give you where to start from, and then using iterative during design, you are able to to refine and get adequate. Even the thickness of these webs, the thickness of this web here are all checked. Even the top flange and the bottom flange, all these cantilever are all referenced in text. So you have to read a lot of text references so that you get everything required. So basically that is what you need to know about the bridge here. And then some further literature here. If you look at this is the what we call the deck system. This is comprising of those parapet, the box girder, which we have talked about. So if you look at it here, these become the this is the deck system. So that is your deck system, and then later on we go to what they call the support system or substructure. So the superstructure deck is where you have the vehicle moving, and then whatever support system coming into water is what we call the substructure system. Then you get the foundation. Foundation now start pile caps and the piles. So if you look at so this is what we would call the substructure system, including foundation. Now this and that support system are simulating or representing abutment, and then these are the pier support with the piles. So basically that is what you need. So it is because of the geotechnical findings, this is going to be both friction and end bearing. So the end bearing simulated in the boundary condition, and then along the piles we have you have what they call the soil structure interaction, the spring constant, to simulate the different layers of soils. So you are able to know the density, whether it is loose, whether it is medium, or it is dense soil or very dense. So you do, and then on the upper part here, normally we consider to be like in water or loose soil, and then depending on the geotechnical stratification layer identification and definition, you are able to know what is here up to the bottom, so you model properly. So this is our substructure system, and then this is now you are doing is coming to the complete bridge, and then that is called. So this is what I was trying to explain, that we have the deck, we have the pier support system, including the abutments that are not included, and then the pile foundations. So that is what I wanted to show. And then once you understand this is how it is drawn here, and then down here is where now we have the pier support system, and then this section is solid in nature. These are the two pier support system, and this is the pile, and this is the pile cap, and that is the crash barrier here. These are the barriers they put, and it is 12. When you remove this barrier, you get effective width of the bridge. So this is the layout of the, so this is this dark one, the pier support, which are these two, and then these are the piles, and this is the 11 by 6. That is what you have. Basically, that is briefly some references between the drawings, what need to come out from the drawing, and the model, because a modeler must understand how the geometry is for you to have the geometry dimensions, so that you are able to do proper modeling. That is when why you have to know you need this one here is another. This is related to what I explained the other day. So here you need to understand the tendon layout, the X and Y. You need to know. So it's also very important for you to calculate the neutral axis of the section, because you need to know this the tendon locations along the bridge has implications on the performance of the bridge. So that will be adjusted until the stresses in service are all within limits. So I told you for pre-stress system, we look at both ultimate limit state and serviceability limit state. So you're going to look at the tension stress and compressive stress and try to balance basing on the way you have aligned and profiled the tendons. So you can see this tendon, this is the continuous. So basically it is very important that you get to know the layout. So that means even here it's very important that when you look at this one and you get to know the tendons, you will find that knowledge of profile is key. You can actually see that knowledge of profile is key. So you need to see, you can see the profile of this tendon. So you really need to know. And there are many text references that will even tell you the cover, minimum cover required for tendons, the different tendon diameters, the minimum and the maximum tendon spacing horizontally and vertically if they're in groups. So that is very, very important that you have to read. It's not just a matter of just doing it. So it's important that to read through and then also try to understand how. So this basically it is each of these have each of the web has tendons. So that's why in plan you can see it. This is the one, this is the two middle web, and these are the outer web. So they are all aligned along the webs. So basically I wanted us to be aware of what needs to be done by an engineer who is doing the modeling. So you can actually see. So even here you see this is exactly what is modeled, but before modeling you need to understand the geometry requirements and get it right, and then you model. After modeling, so when you're doing modeling, what is required, you find the issue materials properties are very, very important, whereby concrete you have to define it, and then the post-tension concrete so these strand details are all defined by the software, whereby you need to know the ultimate tensile strength of the cable or strands, and then also you need to know the area of the strands. Those details are always given. Even elasticity, modulus of elasticity need to be known. So, and then the jacking force, all that when you read, and for those of you who have already done some pre-stress concrete structures, you actually understand these jacking forces, what need to be applied, then the slippage and the wedge. Normally say 6, even 5, or some even go by saying there's no slippage. So these are all coefficient values that need to be considered. These are factors which you need to input in the software. And then for the loading, actually you can see the loading. You need to do about self-weight, you need the pre-stressing loading. These are the requirements you specify. The pre-stressing also is given, and then creep and shrinkage and live load. Even temperature you're going to see. So basically what I'm trying to show you here in the literature is that so many things you need to be well versed with, so that you are able to come here and be able to do a very good modeling. That is very, very important. So that is something that you need in the modeling. We need to have knowledge of the geometry. You need to have knowledge of levels, dimensions, and then the parameters for design. Very, very important. So here for this project, you find that actually if you look, I've always been giving you the procedure, which is not actually different. The procedures are very easy, that you do your material definitions. I told you you have to do material definitions. After you have defined your materials, all that, Then you come to this time for precast system and post tensioning. Don't forget the issue of time dependent variable, time dependent materials I showed you last time. This is for creep and shrinkage. You see creep value, and then when you go to shrinkage, it also gives more negative, while creep gives you more positive. One is progressive with time in service, that is creep, while shrinkage is normally happens when concrete is gaining plasticity and then as it hardens. So some of the things you need to read concrete technology books to understand concrete as it is, concrete behavior, right up from batching, materials batching, transporting, placing, compacting, curing, and attaining. It's very important to understand that, because you see, like post tensioning concrete. If I give you a reinforced concrete and post tension concrete, and I use grade 25, grade 25 is good for capacity, for reinforcement. But if you subject that grade 25 to tensioning forces, and you know these forces are in 1860 MPa, which comes to about maybe 1395 MPa if you use 0.75 jacking force, taking care of all these other loss and the rest, then definitely you'll find that this concrete will fail in by crashing. I told you yesterday that the other day that when you are pre-stressing, you are trying to keep concrete section in compression, and you try to limit crack. But if this compressive force gives you strength higher than the capacity of the member, then it will crash. So that's why the minimum grade for pre-stressing starts at about, I think, 40 MPa compressive, which is about 32 characteristic grade, going to 40, 50, 50, 60, like that. So you need higher, and it's more of to take care of pre-stressing and also durability, because we are trying to limit ingress of contaminants to avoid corrosion of post tensioning members that are holding those concrete members. So that is what normally it is done. Then for time dependent on a concrete compressive effect, you'll find we have this, and it's giving you the mean compressive strength of concrete at the age of 28. That is the characteristic strength plus the other factors of standard deviation and the constant. So that is how you can actually look at it. Then normally you have, after you have done these two member here and this, then you normally have to link. This material must be linked. So you come here in the creep, and what you make sure you highlight the creep, and then you highlight the compressive. You come and transfer this here. You can transfer that in this area, whatever it is. Then from there you add, it will come down here when you go. Then after that, it definitely already linked. If you don't do it, then it will link up. This is very important. Normally you have to do that. So in modeling, then there's that element of cable definitions, cable plotting, and the rest. So I think we shall have a look. So the sections are all defined here. You have the box girder, you have the box girder defined. There are different sections here: single, double, I section. The one of yesterday you saw, it was a T. So you have the I, you have the single cell, 3 cells, all that single box girder. You can define them from here. And then even the solid section towards the end, normally shear is too much, and then you find depending on, so normally it comes down. So you have that. What interesting area again that you need to know is when we are dealing with the cables. You see, you have to also look at the cable definition here. This tendon type, tendon names, tendon types, names can be internal or external. We are dealing with internal, but the current, in most cases, you also have post tensioning done externally that member, and they always say it is even better and easier for you to inspect and manage externally tension members than when it is internal, because when it is internal you cast concrete around, you can't break concrete to know what's happening. So that's why normally now you have to believe in other sophisticated machines and tools to know whether the members in are. So being internal can also be bonded or unbonded. Please read about theory about pre-stressed concrete. Bonded or not bonded, they're also there. The issue of anchorage slippage are all given. The curvature frictions, wobble frictions, relaxations, tendon area, duct, they're all given. So that is important. Then also very important are the profile. You know, now you need to know, that's what I was telling you, need to understand the profile. So you see here, each of these, so now you need to understand tendon names, the tendon group. The grouping comes in when we are doing construction staging, but that one always we can learn as we continue to digest a bit. So you have all that. So if you find you can have a plot of all this, so you can see now when for this one, this is the member which is plotted. So this member here, you must know the X, you must know the Y, the Z or the Z, and then you can see that if it is plotted in the middle, then Y remains 0. But because you are plotting it slightly off the center here, it's maybe 1.5 meter this side, so that's why you see Y is 1.5. That remains constant all through. But then the X must vary because the X is moving along the bridge side, the bridge direction, while the Z is measured from up downward. You see that this one here is coming down. So you have to measure from top to the center of the so you'll find it varying from, you can see here, this is somewhere slightly 1.5, but in the middle has come to maybe 0.2. You can see even here given the Z all even here at 12, it is lower, then it climbs again up. Remember, high tension hogging moment and bending moments also apply. So even your profile has to move in that direction, where you have here you have compressive effect and tension. So you are trying to control tension while also giving in the required compressive force. So you can see these sections are having different locations. So that is why even here is done. So if I give you another one, if I pick one here and say display, you may find it is in the middle here. So it is actually the lowest most here. So you come, if I do all up to here and I say display, you find member running going up like that. So basically different section. Now what happened? This is at construction stage 1 or construction stage 2. This is now where I'm done with support system, and I've started working on the deck system, being a cast in situ. So now you find up to here, I am now trying to put this profile, come over this support, and then also is overhung by certain percentage of this span. This is 45. So even again from your literature reading, you will find that actually normally, but this levels sometimes are guided by point of intraflexure, where you have 0 moment kind of when you use the dead load, or sometimes from because of the many research done and other things, they tell you maybe 0.15 or 0.2 of the span or something like that, but still it's very important for you to look through. So that is normally what goes on. So the issue of profiling, the issue of identifying and laying out the tendons, you must understand first of all how do you determine the neutral axis of the member of the section. You also need to know the different patterns of laying the tendons, both transverse and also longitudinally in the bridge direction. So that is where that leaves us with rooms for reading and understanding in depth about tendon layout and the requirements. So that is something that we need to appreciate, that you cannot just do it. You need to be mindful of how it is laid, the cover, the centers, the spacings, and then both vertically and horizontally, and then the layout, how it is done. That is very important. You can do what they call it can be parabolic or it can be straight, or depending on that, but of course you have to read. But at least for pre-stressing, now you see an element, this one, and also reinforcement. So you're going to find that actually you also expect reinforcement to be, you see now even reinforcement. So this reinforcement together with so you can see the different reinforcement. Of course, these are the ones you find, they are there. And then you have the tendons. So, and also I hinted that when you have post-tensioning, the reinforcement percentage tend to reduce. So I think rule of thumb is about 40, I think 40-60 or 30-70 or something, but still we shall share that knowledge. So basically that is also, the order is very important, but this time you're going to add the issue of also that. So boundary conditions have to be given, the issue of the stiffness and the rest of it. So that is here, and the tendons are all given here. If you want to remove, you can just come here and display. So that is very important. There is also earthquake aspect, some nominal earthquake. That one I don't want to dwell too much on it, but you can actually look at it. Yeah, this is the earthquake. The software has all that. You need to be mindful of the element of ground type. There are all different types here. The type 1, type 2 with different factor user defined. Then the reference peak ground acceleration also is given. The importance factor, the various damping ratios, and everything. There is the Singapore or recommended. Then there are different design spectrum that you look at. So these are some of the additional elements that you need to know in modeling. Having done that, then you go to your traffic. I think here you have to define the lane. Then you have to define your vehicle, load model 1. You can see your load model 1. These are adjustment factor that are all in the literature. Please make sure we read lane 1, lane 2, how you do because lane 1 has, I think, 9 kilonewton per square meter. Lane 2 has it 5, I think 2.2 or 2.5 kilonewton per square meter. Lane 3 like that. Then you have tandem system. Tandem system 1, which is 600 kilonewton total axle. Then tandem system 2, which is 400 axle kilonewton. Then the 3 is 200. So there are like 4 wheels. So if you divide that, you find for tandem system 1, it is 150, 150, 150. The other one is 100, 100, and the other 50, 50. But for the linear, so you use, so the adjustment factor here, if you multiply this by 9 and you multiply this by 2.5, 2.5, so the UDL becomes 5.5. Please read and you'll see something there. So then you also have load model 2. Load model 2 is here. Load model 2 has 400 kilonewton axle. So they're on the 2 wheels. So each wheel is that. So this one always proves to give you worst case scenario when you're doing local effect analysis. How the wheel load affects the performance of a deck section at that particular location in the transverse direction. So it's very important. Then the SV loading, the standard vehicle loading. You see here they talked of 196, but you also have 100, you have 80, you have 250, and the rest. But okay, depending on the road class, and then how busy the road is, the critical linkage could be the normal highway, could be the normal the normal, the inter-district, interstate, the trans-border, where you have a lot of traffic, heavy traffic. So some of this will help you to know and come up with the load that are similar. So here under this load, you also have, if there's footway, you also indicate footway and specify. If it is for fatigue, normally for Midas, I think it is a steel composite for fatigue is there, you specify. If it is rail traffic load, you also, sometimes this deck system combine both rail and traffic, so you look at it. So this is another. Then you also need to take care of settlement. Settlement has the implication on continuous bridges with the support system. So settlement is important. You have to specify the settlement here. Normally it's about 10 to 12 for piles, millimeters. So you should be able to do, if you think it is going to be on this side, you can specify and see the behavior, or you can also do for this, you see if it's going to cause problem, or the pile here, or you can do for abutment pile system and one pair, you see the behavior, or you can zigzag by using this extreme, this outer one and inner here. Still you look at the worst case, so you can able to do that. Now construction staging is very important. So construction staging is now where, because I think for precast pre-stress system, the use of time is also very important. Stages, there are different stages of construction. Sometimes these girders are precasts, so you have to find a way. You first precast. From there, you have to allow it to dry or to harden up to maybe 90% of its 28-day compressive strength. From there, then you're supposed to begin applying the cables or tendons. So the tensioning sequences and final tension forces should balance with the compressive and tensive effect of the concrete. So because of that, the use of time is always taken care of, and the sequence of your work. So it is very important that when you read, you get to know a lot more, and we shall share. I will look at some of the literature seen, then we shall be share. We shall spend some time on this. So let us not get discouraged. I'm also learning. So now, if you look at the construction stage 1, it will be for you to do. You have already fabricated your site. You have where you are cutting your reinforcement. You have the reinforcement cage, the fabrication yard. Then when you do your drilling here and the rest of it, normally we do after pile cap. We do the first piling, then after pile, then we go to pile caps. Then from pile cap you start working on the pier support. So here is where you need to be careful here. That let me see how best we can do a demonstrate. I think there are 3 stages or 4 here. So let me first remove this spring constant from the pile system, so that become clear, and then we can quickly boundary it here. I can do that, and then I do the So I think my first stage, just for purposes of, you can also indicate the support system, because I had removed them. So these represent the abutment, and now this is so. Otherwise, you would first do we would do our pile up to here. I do some pile up to there, and then I would that's what I would do. Then later on, I do my pier support system. So this is the substructure system, including pile system. After you have done all that, it has set, you have prepared the props. This is going to be a road one. The road is going to be in the middle here. Actually, from here, if you can refer to that, you see this road. This is the support. This support. So you have to first make sure you work on this. Then later on, here you do up to certain point to allow traffic to move. Then again, you will now do traffic movement here, diversion here, and also here while you work here. So in the model also, you try to relate. So in construction stage 2, That is where you are. So your construction stage 2 does not just do the middle part here and here is for this one here. This is the one for the where you allow traffic to move. You don't put anything. So the propping system will be from here up to here. So you have a prop system here, and then also you have a prop system here. So you do some barricade here, allow traffic to move. That is construction stage 2. Would have been 3 if we do first up to pile, then you do this pier, and then but I've done it up to that, and then so 3 is to have these 2 support. Then the third one is where now you now open this area. You after the concrete has gained the strength, you now open this area with steel constraint. Then you allow diversion here, which is demonstrated here. You allow traffic to move here, and then you create here, which here now is this side and that side. Then now you come and do your third stage. So now this area now will have prop system here. You have prop system here. So now you don't allow traffic to use anything in this area and this area because it will cause problems. So you just come and create also a very good adequate 6 meters here. This is 30 almost, so you can create even 2-3 lanes. Even you can create even all. You can decide to use 1 or 2. So now this is where construction stage can help you in a river area or a busy road section. That's how this is done. So we do, and we are done with construction. So that is how construction stage is very, very important. It will help you not to interfere with the business in the area, or also the water if it is in case of river bridges, you try also to play around. That's where we bring in the precast system. You first do normally for river bridges we limit the use of support system like the propping, because it's very bit expensive to do that. So that is what is done. So that is the most interesting part, is how do you, and because of this construction staging, that's where the issue of time dependent parameters here, they have become very, very important. Time dependent parameter become very, very important. So time dependent material function, very important. You need to know that, otherwise if not it can cause problems. So that is how we look at this. And then we come to, I think after you are done with all that, then you can now go, you apply the loads, the different loads. Self-weight loading, you have done all your model, you have done everything. You can actually run tests using self-weight, but the self-weight, for you to run, you first need to come and make sure your self-weight is defined. You see, your self-weight must, you always make sure your self-weight is defined and is taken care of. You get it? So your self-weight has to be defined, and make sure it is Z is -1 to face downward. And then because of construction staging, then it has the load case also, the load group is there. You have to make sure it is there. And then load group is here, load case name also is there. And then you're able to make sure it is given. So once you have that, you have done everything. So this is the most important thing, is to do all construction stage, and self-weight must be done. Once you have done self-weight, you can run a test, and once it runs, then you know your model is. So you can also do some calculation to check that the reaction you get due to self-weight matches, except for the dead load, for the deck system alone. You can quickly check for the deck system, and also you check it all the way down here. So now having checked, then you can now come and start. You start now putting. Make sure you define this. This load group also define. Make sure you define this. Normally we come to the loading, and you find that anastatic. You can do the load cases are all here. You have construction staging, self-weight, superimposed dead load. Superimposed dead load will include this one here. Anything that has element like the asphalt, concrete, parapets, raised walkways, any services to be done, those one will form what we call superimposed dead load. The dead load that comes after, when the permanent load has already set, and then you are going to do So those superimposed dead load normally, like for the asphalt concrete now, is the one to receive traffic, while the parapet and cross barriers become the safety parameters or safety aspect or safety items that need to be used. So you have to do that. Then there's tendon, there is construction loading, which is normal equipment, life load like from human being, and other things. Then you have the temperature rise, the temperature elements, basically that. And if you want to apply wind, you can also do wind. So basically that is what you really need to take note of. We have temperature, element temperature, you have the temperature rise, temperature fall, construction, they are all given here. Like I think for temperature rise, what would be, that's how the whole thing is. Does it have a property? I don't see property that would have. So for temperature element, it will give you different behavior. You can see it, I think, having different. So it's just given it as one. The other one, the way it appears, they have different response and the rest of it. So you have that. We would have also had like superimposed dead load has elements as quite a number. I did not, so that's how the whole thing. You see, it's almost 120. It means you have to put asphalt, concrete, even sometimes this one doesn't have permanent formwork, so you put services, and then you put parapets, all because it's done as a solid or a linear. You just converge all and put it on that one. So that is exactly what needs to be done. So superimposed dead load has quite a number of dead loads that are put together. Okay, so that is what we need to do. So if I can take you this side, you find material is defined, loads are also here done, defined, traffic is done, creep and shrinkage, you see the type of cement, relative humidity, temperature, age of concrete at the beginning, all that are already part of what I showed you the other side. Live load, for here they were using Korea, so you can see this is the kind of load they applied. Then in the modeling, this is also very important, I want you to be aware. Someone will say, where do you start from? What happened? So there are two stages here. There's setting your model for the software to do the modeling. Then you are doing creation. So under setting, you have to save the project files. You have to do setup of the units. So I can quickly take you back here. You have to saving. Here is where you do the saving. You can save it somewhere. Then for setting, you have to you have to come to the tools, come to units here and do the settings here. I have actually explained. Now here normally it's the Fahrenheit, but it's good to go to, even if you leave it Fahrenheit, but you need also to convert your temperature to Fahrenheit for it to be uniform. So that is what you can have there. Then what more is it telling us to do? Set up the structure to 3D or 2D, that's okay. Input material property, I've given you the material properties given, concrete, steel, tendons, all that. Then section property, this one we have been singing a lot. Then define time dependent material property, I've given it very clearly here. You come back to the properties, creep is here, actually it is here, time dependent is here. If I right click, it gives us straight here. This is now your creep and shrinkage. You just put on the one, then you go for concrete compressive here, then you also do the same. That is this is for compress, where you have to be aware always. This code is very important. Make sure you don't change them. And then you see now cement type can be rapid hardening or normal. Get it? So very important. And redraw, this is what you get. So you have seen they already explained somewhere there. Then define. Now when you come to creation, now you create a model. The shape, node, element I've also demonstrated. Even when we were doing box culvert, it's not different. All the different software you have, you never move away from some of the things here. You don't move away. It's very important. Defining the group. I've actually given you, let me show you where the groups are. Once you have done all this now, and you have now done all the models, for you to go to construction staging, you need to first group the members. So you come here in the grouping, and it is actually this first part, the structure is you make sure you click and you put a new, and then you type substructure. So if you see that's my substructure system. If that is your substructure, I showed you that's our construction stage 1. So now you group it. So if I wanted to make sure this peer support and the peer cap were supposed to be construction stage 2, I would now do substructure 1 piles up to pile cap. Then number 2, I would do peer support and peer cap. Then I move to deck system. That's what I would do. But here I decided to make it all the way here, so that is it's not going to make a lot of changes. So now that is what I will do, and then I can take it back. Then if I want deck system, so I told you that this deck system, this is over this. So you are going to do the outer span. You leave the middle portion of the. This is 40 meters. Even though this is 66 or 99, you still have a lot of span here. Traffic will continue moving. So that is now that deck. So you can do it both sides, or you could do one and then you just continue. But I decided that since it is in a dry area, you can actually prop it. The contractor has capacity to do all that. So you are able to do now that's the deck 1. So that is deck 1. So deck 2 is now here. When now you have diverted traffic on this direction, you are able to remain with the middle deck. So you can now prop it, work on your reform work on reinforcement, work on the tendons, and then casts, and then tendon it. You tension it after it has gained that minimum strength you want. So then you make sure always you do all. So you are doing first 3 stages differently, but then at the end all will be working as one. So that then you also have to do the foundation. You see these are the foundation system. You see now it is all appearing, all have been captured. You make sure you group it also. Then the rigid links, the rigid link must also be grouped. Elastic links must also be grouped. So, but of course you need to understand why you use rigid link, why you use elastic link. These are things that we shall learn as we move, and as you also understand the behavior and mechanics of bridges. Very, very important that you understand the mechanics of bridges. So the load grouping are also here. So there's boundary group, load group, and structure group. Structure group are now the piles, pier caps, pier system, abutment, and then pier caps, and then deck system. While boundary group will be the foundations, and then these foundations sometimes you connect them using rigid links. So that's how the rigid link comes. Then elastic link normally appears where you have the bearings. This elastic link can also be rigid in a way. You can actually come to the boundary condition. This is where the rigid links are. That's how you have to, and make sure it is defined. So the group must be defined before you apply it. Then I can still use my elastic link as rigid link, but I make sure when I do it, you see here is asking me if it is bearing and I want to put some values. I need to know the spring constant to define here. Or I can say it is rigid. I can come and put rigid. So all that have disappeared. So that means when I give this condition, it's going to have similar behavior when I use this normal rigid link. Very important to take note of that. Okay. Thank you. So they are quite. This work is procedural, steps wise. You need to understand the different steps, and the good thing the user. So the software manufacturer has a lot of literature on what to follow. Mine is only to give you confidence that if Michael can do it, then you'll do better. Because I'm just touching few areas, and you can go in there. So here you can now put your structure boundary, then the loading, input boundary condition I've given you there. But this boundary condition must also be in line with the way the structure grouping will work. If I do my my construction stage 1, the boundary group done, the boundary condition that need to apply will be all, this one all have to be in place already. Even the one for the spring constant also will be in place. So Anna construction stage 1, this one you need to have. Then when I go to construction stage 2, where now, you see, it means my boundary connection here has to be in place already. All that, you get it? So the connectivity here, the rigid link here, because this deck has to be connected to the PR support rigidly. We are not going to have any bearing. If we are going to have bearing, I would have elastic link somewhere connecting on top. So this one is going to be rigid. So that is very important. So the grouping goes hand in hand with the constructions and boundary. When I'm doing it, all has to be there. So that is something that we need to follow, and that's what. So the loads also, even the loads, you have to put loads in accordance with how the groupings are here. You see, you have your self weight. So if I'm putting my self weight, must be in together with this one. SDL, the superimposed dead load, must be together. Temperature, mark these two. There's temperature gradient and then there's temperature. So the temperature element goes with this one, while the temperature gradient goes. Then the construction, tendons and other. And if you want to have even these tendons, all these tendons are also given. If I go to loads and I want temperature pre-stress, and I come to here, not this one, it's here, tendon. You know this tendon, if I want to modify this tendon, it takes me to group, name, properties, and you have to highlight. You see this already highlighted. So that has to be there. It has to be together. If you don't put this group, you will not run. So everything now, when this now in the construction stage, the definition, you have to make sure they're all defined. Profile are all given. Then when the most interesting thing, you can group it, but you must transfer it to the analysis section. Where so you have to know now it has to be tendon. Then from there also make sure it is tendon. Then you highlight all these tendons which are all here, transfer them this side to the selected area, tendon to the selected tendon comes here. Then you also need to, you see when I click on one, this property, this is already selected, highlighted and brought here. And then the loading stress is here, begin and end. So meaning you are doing on both sides, you're stressing, but sometimes you can stress from one direction. Okay, so this is very, very important. Now you have done all the model loading. Now you do the construction stage definition, the grouping, and then giving all those assignments. So having done all that, you've done your traffic, everything, then you run the design. When you run the design, then that is when you begin to see so many things happening here. You can now see, having done that, you begin to see different images. This was the images. These are the different images. This is a section. This is pile section properties. Then you have a section here is given section property. I think there's one which is at the support, one is at the, when you look at this one, it will give you some clue. One is deeper, the 2 meters and the 1.35. So it is tapering. Just look at this area. If you look at this, is tapering. This is more of straight and then linear. It's not parabolic. That's how the choice was made, but you can still modify. So this is how you look at. Okay, fine. I can still go on further here. So this is now saving the project files. I explained to you that. Then units, I also explained. You go to tools, you come to the unit, you can specify cells here, everything. Modeling can start. Use a 3X, Y, Z, X and Z. This is for 2D. Then you can do the 3D if you want. You can model. And then this is how you define your the tendons. This is now sections. Then again you model. This is the quick definition. I've already explained. This is now very simple. This is how you handle your creeping system. Time dependent is here. You see the order is here: saved, set up the system, set up structure, input material properties, input sections, time dependent. Don't forget, it's very important. Even when you're doing steel composite, please don't forget that. It's very normally we forget it. Then you have create models, defines. For steel composite, you can even do it first. Then before you do other loading and run analysis, you can do it, and then make sure it is linked. Then your input boundary, input load, and define construction staging. So you can do the construction staging, you get even your output, everything, but now then you do what they call post-tension. So there is what they call, there's something I put down. There's modeling. When you do modeling, the jargon of materials, sections, boundary conditions, all other things, and testing even if you want, using self-weight. Don't forget to put self-weight. In 2006, we were designing the headquarters for Yonra and Ministry of Works. I was engaged by Multiconsult Norway as their structural engineer assistant. So my role was to do design of staircases, the decks, the slabs, the roofing, and the rest. While the Norway gurus, the seniors, were doing the frame system. And so they use STAT for modeling. So one day now we were trying to discuss with my senior. He had done design close to 6 months. So he was trying to take me through to understand what he has done. So when I was trying to look at, then he discovered that actually when we were checking the different loading, the screeding, services, and live loads, then we discovered he did not activate the parameter for factor for the aspect for self-weight. So when he put the self-weight on, whatever he was designing for 6 months failed. So he thinks that to start again. It's very important. It's very, very important. When you're doing it, don't forget. So that was the experience I got. So this is now the compressive. Now the linking is even here. I told you. You see now here you link using these two. Before, so if you don't link, that means your material, time-dependent material, is not until appear clearly. So that is, you see now, this is now extruding, doing its own set. So setting is done. It's going to create now the model which we have been doing. So I'm just only zigzagging here, swapping, so that we just see that these things are not different. So you come down here, sections are given. Now this is how your self-weight behavior is when you run your model now. So you have your friction pile, friction and end bearings. You have the reactions here. If we had our abutment in place, this one would have gone like this one. But because it's not there now, I can use this loading here to design my abutment. So I can model abutment separately. Yeah. So basically, you're going to have that self-weight. Then you have for superimposed dead load. You can get all that. Then you have for temperature rise. You have for temperature fall. You have for tendons. You have different loading giving you all that. Now this is now when you have run your model. You have modeled it, you have run analysis. So now this is now load case 1. So this one I can demonstrate for you. So I can go here, results, and then I want to see moment. I do that, and then I want for load model for load case 1. So load case 1. So when I add the second load, the load start to build up. So you can also view the legend where all is given. So basically, so this is not. It has also. But the only thing is it doesn't show both the end condition and the frictions. So the spring constants, and then these are all along here. So that's why you get this behavior well. So this is how. So if I go to load case 2, you can see you can see the behavior is changing. Then even the loading here will have changed. If you view the axle load, you can see how it is. So so that is what you can easily look at. You can look at load case 3, and then this is the shear, and then you can look at moments, and then yeah. So the different load built up, the load cases will be building up separately depending on the time and other things. So basically that is how you would actually look at the different. Now I was telling you that even settlement has implication on the behavior, so you can actually look at this is the load due to settlement. So it has its own behavior. Even temperature has implication on the behavior. Even your tension and tendons. You can see how it is the implication. Earthquake gives you different behavior. So there is earthquake in the direction of the bridge, and there's earthquake perpendicular to the bridge. You can see the behavior. So and so I can also try to look at how would it behave. You can see the behavior of different. This is the behavior of when this is now in load combination, and this is how the whole thing behaves. So what I'm trying to zigzag on is for you to look at the different behavior here. So these are the all different behavior coming down, and then down, looking at the different load. And this is the earthquake behavior. These are the live load behavior. These are the envelopes of live loads, shear, different, coming all the way down. Yeah, so this is what I tried to explain already. So this is when end bearings here, and this is when you have the skin friction behavior. Yeah, basically that is what you could actually see and get to know. So at least today I've tried to do more, just to discuss basically on modeling. So all these are the different behavior. The concepts are the same. So you can see this is now when you're dealing with tendons. You look at the input envelope, the pre-stressing. You can see this flow diagram, tendon property, tendon profile, and apply pre-stress. I explained that here. I explain it here. You come to, let me first go back to post, and then I come to load, temperature pre-stress, and then temperature pre-stress is here. You know there are tendon properties, then you come to tendon profiles, then you come to how do you apply this load. I explained that to you. It's exactly what here is being explained in a nutshell. Don't even worry about that. So it is actually here for you. Temperature, then you come in here, tendon properties, which you already defined at the beginning. You have tendon profile, then you have the forces. It is here. Adding all this. The next one is now, this is for profile. That is property profile. And these are actually here. So he's trying to demonstrate how you can input all this. So that is exactly what I think I need to explain that to you. And then I can bring you back here in the processes, modeling steps. And this is very important for me. I think for some of you who want to learn MIDAS, this is where you need to handle carefully. And then when I come back here, this is where the model is. And then I've already demonstrated to you the output. Next time we shall look at the design. For design, we're actually going to come here. This is where you look at the parameters. You define all your parameters, consider all tendons if you want, put the strand system, all that. After you have done that, you come to the next one. Make sure you define all these parameters are defined, and then when you define all that, you go and then you highlight. You could actually say, since we are post tensioning this member, you can either highlight the whole of it, or you can pick a portion, and then you guide the software to do that now. So you can now see that I don't have, this is the only part we are tensioning. So you can have this one, and then we have it here, which is this one. Then if I select now all, I've selected it, then I can design output. How I want it to be, whether it is going to be in both the I and J or none, or I or J or I and J. You can apply that. The same apply to the output. Then you come to serviceability conditions. Since this automatic has been selected, but you can also do your own thing on quasi, frequent, and characteristic. If you're doing BS, it will ask you differently, so you need to be aware. Then from there, the short term, long term, define here. Exposure clash, I told you we have to be careful. Here it could be XD1. We need to find, let's go to the concrete references and read and get to know. And then also for practicality, most of the sites have chemical testing. You need to know durability is governed, cover, and the rest of it is the exposure condition matters a lot. So you need to cross check and know what cover you're doing and the rest of it. So shouldn't be a problem. Then from there you come and click on perform. It will bring you this parameter. Then you come and view. Check the flexure. It's giving you all these results. Then you check shear. Of course, now you're going to find that it has failed in some area. You adjust. You see these rates need to be adjusted. You continue. Make sure combine torsion and dot. Some areas have failed. You have to now do what is required. You see some areas have failed, which is very healthy. And then you come to make sure the tendons don't have their limits exceeded, the tension. They are all here. You check, then you come to construction. At service, you see it is failing in at service stage. So how do you make sure the whole thing is correct? But at construction stage is passing. So it means you may find that the tendons are fewer, can only handle construction load but doesn't have services. Or if your construction load is very heavy, then you may find that it is over designed for the in service. Maybe the traffic load is far less, so you have to also try to strike a balance and see. Or you may find that the layout is not right. You need to adjust, or the section need to be improved all through. So crack width also checked here. You make sure all these are passing. So this is now where you can just keep adjusting so quickly. That's what normally happens. But the most important thing is, and by the way, I forgot to explain, this is where you get your construction staging. This is where you get construction stages. There's element, there's boundary, there's loading. So you keep looking at what happens here, even the loading, what happened here in the first stage, second stage. So you need to be careful. So I think in the next example, we shall try to do a simple one and do modeling together, and then and see how best we can handle, so that we all learn. I also need to be also an expert in this kind of thing. You know, sometimes I borrow my experience right from my secondary. When your assignments are given, I always make sure I participate in the presentation, because when the time for tests come and exam, I don't have difficulty in making reference, because if I was the one standing before my colleagues and presenting, I always recall and try to put things right. So this is basically what we need to take up today. We shall continue and then share more in future. Thank you so much. God bless you.